So, in dealing with the subject of metallic bonds are different from ionic compounds. Did you ever wonder why it is that metals are really the only substances, the only elements, that can bend and retain their shape? So we have a piece of copper, and we can bend it, a little firm, and it'll retain its shape. Okay? Well, even other elements in the periodic table. Lead, for example. Lead's very easy to bend. It's very dense, but it's easy to bend, which is why Romans used to use this to make pipes out of. Retains its shape. It bends. Doesn't break. Aluminum, you're all familiar with. Aluminum foil. Okay? Bends. Can make all kinds of shapes. Okay? If something is bendable, metal's bendable, and you can retain shapes out of them, that's something called malleability. They're malleable. Means you can bend them into shapes. Metals are the only ones on the periodic table that have that quality. And the answer is because of metallic bonds. So what would metallic bonds look like? Well, let's say, for example, let's take our piece of copper. Copper is also, as you know, very good at conducting electricity. And it's because of the bonds inside of copper and the way the electrons are arranged that allow for it to be malleable. Okay, here's what I mean. Inside of a piece of copper, you have a bunch of copper nucleuses. And each one of these nucleuses, we'll just put copper, as you know, have protons. And the nucleuses themselves are all positive because protons are positive, so they're all positively charged. Maybe they're +2, maybe they're -2, we don't know. But they're positive. Copper, on the periodic table, it's a transition metal, generally has 1, maybe 2 valence electrons. Okay? And those electrons are not transferred like an ionic bonds, but they're shared. But they're shared in a unique method. They're shared in a unique way. They're shared all over the place. So electrons will move and migrate, and they're shared equally, and each one of these copper nucleuses are surrounded by at least 2 valence electrons at all times. And because they're surrounded by these valence electrons at all times, all of them, it creates this vast, what's called a sea of electrons. So it's like these copper atoms, these nucleuses, are swimming in a sea of electrons. So that is the model of metallic bonding, and it's what makes them become great conductors. And it's also what makes them malleable. Here's why. If you apply a force on one end of a piece of copper, that force applied to the end of it will be shared equally among this network of copper atoms. So it's like it's dispersing the force that you're applying to one end, and all of the atoms are sharing the load, thus making it very difficult to snap in half. So all of these electrons are sharing the load, okay, and they're absorbing the force that you're using while still staying connected to one another. So it's like a gigantic chain, an almost infinite chain of atoms, held together by the swimming sea of valence electrons. And because the electrons are moving so much, it's very easy to conduct an electric charge through them. It's an electric field can easily move, okay, be set up through the electrons and through the positive nucleuses. So you have this sea of electrons, delocalized electrons. They're called delocalized electrons. Delocalized. So that's what makes them great conductors, and it's what also makes them malleable, being able to bend and not break. And these are metallic bonds. Okay, and you see them mainly in the transition metals, some in the other transition metals, and a little bit in group 1 and group 2 metals. But metals are malleable because they have a sea of delocalized electrons, and they're the best conductors for that same reason.